In this video tutorial, we will talk about line diagrams. So before we begin, let's do a brief review of chemical bonds. The noble gases of group 18 or 8A are extremely stable or unreactive due to their full valence shells. To achieve stability, other atoms will either gain or lose electrons to achieve a full valence shell. The stable ions are now said to be isoelectronic with the noble gas they are closest to on the periodic table. So what I'd like you to do at this point is press pause, try out this section over here, and press play when you're ready. But let's go over one example together. Sodium is in group 1 of the periodic table, so it has one valence electron. Now, is it easier for sodium to gain 7 more electrons in order to turn into argon? Or is it easier for sodium to lose 1 electron and become neon instead? So obviously it's easier to lose that 1 electron and become isoelectronic with neon than it is to gain 7 electrons to be isoelectronic with argon. So we write down that sodium will L1 lose 1 electron in order to be isoelectronic with neon gas. Alright, so press pause and try the rest yourself. When you're ready, press play and let's compare your answers. Alright, and here are the answers. Take a look at beryllium. It would need to gain 1, 2, 3, 4, 5, 6 more to get to neon, or it can lose 1, 2 and pop up on the other side as helium. So it's easier to lose 2 and become helium. Phosphorus can gain 3 electrons, 1, 2, 3, in order to become argon, or can lose 5, 1, 2, 3, 4, 5 to become neon. Obviously it's easier to gain 3. So gain 3, become argon. Iodine, much easier to gain 1 to become xenon than to lose 7 in order to become krypton. So gain 1, turn into xenon. While oxygen can gain 1, 2 to become neon, or lose 6 to become helium. So gain 2 to become neon. Alright, let's just move ahead now. Up until this point we've been drawing a lot of Bohr-Rutherford diagrams. So sodium is in period 3, 1, 2, 3, so it's got 3 electron shells. So 3 electron shells, and it's in group 1, so it has 1 valence electron. So 1 electron in the valence outermost shell, while the other inner shells are all filled up. But when it comes to chemistry, the core electrons rarely change. It's mostly the valence electrons that participate in the chemical reactions. Since they are the most important, we can ignore the core electrons and just draw the valence electrons. This is known as a Lewis diagram or a Lewis dot structure. It is a lot faster and cleaner to draw it this way. Alright, so try out these remaining elements, draw the Lewis structures for them. Press pause, and when you're ready, press play and we'll take it up together. Alright, beryllium is in group 2, so we draw 2 valence electrons around its chemical symbol. Phosphorus is in group 15 or 5A, so it has 5 valence electrons. Just like in the Bohr-Rutherford diagrams, I want you to draw them in the north, east, south, and west locations, and then start doubling them up if we need to. So there's our 5 electrons. Iodine is in group 17 or 7A, so it has 7 valence electrons. So 1, 2, 3, 4, 5, 6, and 7. Oxygen is in group 16 or 6A, and that is what its Lewis diagram would look like. And these are the remaining answers. Now, as we saw earlier, atoms will try to lose or gain electrons in order to achieve stability. With sodium, we could either lose 1 electron to become stable, or gain 7 to achieve stability. What's easier? Obviously, losing an electron is better. With sulfur, it can either lose 6 electrons or can gain 2 more. What's easier? Well, obviously gaining 2 is easier. So here we have one situation where an atom wants to lose an electron and another atom wants to gain electrons. So one man's trash becomes another man's treasure. Here we can draw an arrow to show the sodium is giving up its electrons and transferring it to the sulfur. And once the sodium loses that outer electron, it now has that full valence shell, and it is now a sodium cation with a 1+ charge. However, once the sulfur gains this electron, it's still missing 1 more electron to achieve that full octet structure. So would it be more helpful for me to add another sodium atom, or would it be more helpful to add another sulfur atom? If you're not sure, try them out. Adding another sulfur doesn't seem to be very helpful, because this sulfur needs an electron, and this sulfur needs 2 electrons, so they both want electrons. But if I add another sodium, This electron can then be transferred to this sulfur, and now everyone has achieved a stable structure. The sodium is happy because it's given up its electron, so is this one. And this sulfur is also stable because it's gained the 2 electrons to match up and get a full octet structure. Now this is just rough work. In order to get full marks, I need you to clean this up. I can accept this as the final answer. Notice how we've organized electrons into 4 areas in order to spread things out. So north, east, south, and west. But you can also draw it this way, where a single line represents a bonding pair of electrons. So all we've really done is just connect the dots. You'll also note that I used dots and X's to represent electrons. The X's are for the electrons that belong to the sulfur. The dots are for electrons that belong to the sodium. This is how I can differentiate where those electrons originally came from. The last option is to just draw a square bracket around it to show that these are now ions, 1 plus charge. Sulfur is also an ion. It's gained 2 electrons, so it's got a 2 minus charge, and sodium lost an electron, so it's a 1 plus charge. Just make sure you don't draw it out like this, because at this point it looks like the sodium is attached to the sodium, when in reality the sodium must be attached to the sulfur. Sodium attached to sulfur. Don't put the 2 sodiums side by side. Alright, so what I would like you to do is try it out for these remaining examples over here. Press pause, and when you're ready, press play and we'll take it up together. So calcium is in group 2 with 2 valence electrons, while sulfur is in group 16 with 6 valence electrons. So calcium needs to lose 2 electrons, while sulfur needs to gain 2 electrons. So that was easy. Now let's clean it up. And we have 2 lines to signify this attachment and this attachment over here. Again, you could also draw it this way or this way. Alright, so here are the remaining answers. I only showed it using the line diagram method. I didn't use the square brackets or showed every single electron. But again, either or is acceptable. Alright, so now we've seen ionic compounds and how to draw them using line diagrams. But what if it's a covalent compound? How do you draw a line diagram for that? They'll typically involve hydrogen and carbon atoms, which is why we call them hydrocarbon line diagrams. Now here are some hints and tips on what you can do in order to draw these line diagrams properly. The first is to use carbon as your backbone for the structure, and typically the carbon atoms will be linked together. Don't forget that all atoms in your structure must share electrons to achieve a full valence shell. That's the whole point. They want to achieve stability by getting a full valence shell. This full valence shell is known as an octet structure because typically you'll have 8 valence electrons. The only exception, of course, is hydrogen and helium, which only require 2 because the first shell can only hold 2 electrons. You're also not restricted to just single bonds. You can also use double bonds and triple bonds if necessary. Now, as you'll see in a little bit, hydrocarbons will often exhibit something called isomerism, meaning they have the same chemical formula but different molecular structures. As such, many different answers are possible. In future courses, you will learn how to use formal charges to determine which structure is most stable and most likely to exist, but in this course, as long as your structure fulfills these requirements, I will give you full marks for it, even if it doesn't exist. Lastly, many of these chemical formulae are typically written in a way that provides the reader with a visual hint to what its structure is. So let's try the first one together, C3H8. Now carbon is in group 14 or 4A, so it has 4 valence electrons, while hydrogen is in group 1 or 1A, so it has 1 valence electron. As we mentioned before, carbon should form the backbone of your structure. Try to link them together where possible. And now I just need to add the hydrogens to complete the picture. So remember, hydrogen needs 2 electrons to be stable, so 1, 2, there that is, 1, 2, 1, 2, 1, 2. Every single one of these hydrogens has 2 electrons available to it. Carbon, on the other hand, requires 8 electrons to achieve stability, and look at it, every single one of these carbon atoms has 8 electrons surrounding it, and they're sharing their electrons in order to achieve that octet structure. Now again, this is pretty messy, so I'm going to replace these dots with a single line to represent the bonding pair of electrons, so each line represents 2 electrons, and that makes things a lot cleaner. Give this one a try yourself. Press pause, then press play when you're ready. So following my hints, you probably drew something similar to this. Use carbon as your backbone, and make sure every element has the right number of electrons. Hydrogen should have 2, and each line represents 2 electrons, so each of these hydrogens is fine. Carbon should have 8, and since each of these lines represents 2 electrons, 2, 4, 6, 8, every single one of these carbons has that full octet structure. But of course there is a problem. C6H12, I should only have 12 hydrogens. I've got the right number of carbons, but I have 14 hydrogens, not 12. I've got 2 extra ones. So I'm going to randomly delete 2 hydrogens, but that leaves these 2 carbons missing an electron each. Well, if these 2 carbons can't find a hydrogen to attach onto them, perhaps they can attach with each other. And now that they're sharing electrons with each other, they now each have 8 electrons. 2, 4, 6, and 8. 2, 4, 6, and 8. So remember my third hint, don't just be limited by single bonds. You can also use double and triple bonds if necessary. Now, did that double bond have to be located between these 2 carbons? No, I could have placed the double bond here, or here, or here, or here. That is called isomerism. Same chemical formula, but totally different structures. So if you had placed your double bonds anywhere over here, I would still give you full marks, so long as each hydrogen has 2 electrons, a full shell, and each of these carbons has that octet structure, a full shell as well. It's still fair game, you get full marks. Alright, let's try this one together. Again, press pause. When you're ready, press play. Now the first question students will ask is, why is the formula written this way? Why not just write as C3H6O? That's a lot more condensed, it's a lot neater. Well, as I mentioned before, chemical formula are typically written in a way that provides the reader with a visual hint to what the structure looks like. And that's what this thing is doing over here. It's trying to give you a hint on what the structure looks like. So when I see CH3, I see CH3. Next, it says there's a carbon. So I'll draw a carbon over here. Then it says there's an oxygen. And then I draw another CH3. But now there's a problem. This carbon is stable, 2, 4, 6, 8. This carbon is stable, 2, 4, 6, 8. This oxygen is stable, 2, 4, 6, 8. But this carbon is not. It needs 2 more electrons. 2, 4, and only 6 electrons here. So I know the CH3s seem to be fine. I need to rearrange this part though. Let's try keeping the carbons together, like one of our hints recommended, and put the oxygen up here instead. Now this carbon has 2, 4, 5, 6, 7 electrons around it. Close, but it needs 1 more. While oxygen needs 1, 2, 3, 4, 5, 6, 7. It also needs 1 more. So perhaps I can bring this electron up here instead and share it with the oxygen. And now it will form a bond with this one and this one, creating a double bond. Now let's take a look. This carbon now has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And this oxygen now has 1, 2, 3, 4, 5, 6, 7, 8 as well. If I clean this up, I'll end up with something like this. Now some students usually start freaking out at this point, going, how? How did you know to do this? I never would have guessed that. So I ask my students if this means anything to them. And usually in my class, someone will say, Hadouken! Hadouken! If you've ever played any kind of Street Fighter or Mortal Kombat or any kind of game like that, you know that down, forward, push, and the punch button gives you a special move. It doesn't matter what fighting game it is. You move the controller like this, one of the characters in that game guaranteed has a special move that uses this. But how do I know that's true? Because I've played a lot of video games. Well, same thing. How did I know that this was a possible structure? Because I've done a lot of practice questions. I don't expect you to know every single possible structure, just like I wouldn't expect you to know every single possible special move in every video game ever, but with enough practice and exposure to different types of molecular structures, you will start to see patterns as well. So from this chemical formula, you've learned 2 tricks. Trick number 1, CH3s look like this. A carbon surrounded by 3 hydrogens. Trick number 2, the formula is usually written in a way to help you visualize what the structure looks like. So CH3 on one end, CH3 on the other end, and a CO in the middle. And finally, the last trick, you can have a C double bond O. Alright, so let's try one last one together before I set you loose. As I mentioned before, these formulas are written in a way to help you visualize what the structure looks like. So rather than condensing it into this format over here, they purposely spread out the atoms so you can see what it looks like. So let's follow their hints. We have hydrogens on either end. So I'll just start on this side first. After that we have an oxygen. While hydrogens have 1 valence electron, oxygens have 6. We then have a carbon, and carbon has 4 electrons in the valence shell. This is followed by 2 oxygens and a hydrogen. Now every atom should have an octet structure with 8 valence electrons, except for hydrogen, which should only have 2. So the hydrogen is happy, it's got 2 electrons here. This oxygen is stable as well, 2, 4, 6, 8. So are each of these other oxygens and this hydrogen. The only one that's missing an electron is carbon, which has only 2, 4, 6 electrons. So that shows me that something's wrong. Looking back at this example, we saw that we could put a C double bond O. So that was one trick that we learned. So let's try applying it here. I'm going to take this blue oxygen and put it on top. And then I'm going to move these guys over here. Alright, so let's just recap. The hydrogen's fine, 2 electrons. This oxygen's fine, 2, 4, 6, 8. This oxygen is still fine, 2, 4, 6, and 8. And so is this hydrogen with a 2. This carbon, however, now has 2, 4, 5, 6, and 7. While this oxygen has 1, 2, 3, 4, 5, 6, and 7. Which means this oxygen and this carbon, they both need one more electron to share. So we'll now bring these two guys together. And now we formed a double bond. Let's recalculate. 1, 2, 3, 4, 5, 6, 7, 8. So this carbon has now got the octet structure. 1, 2, 3, 4, 5, 6, 7, 8. Now this oxygen also has the octet structure. I can now clean this up a little bit. And there we have it. Now this is another trick you've just learned. In general, whenever you see a COOH in your chemical formula, this is usually what it means. A C double bond O with an OH. And this pattern actually has a name. It's a functional group called a carboxylic acid. But you'll learn more about that one in grade 12 chemistry. Alright, so I want you to press pause. Try the rest of these questions out yourself. When you're ready, press play, and we'll take it up together. Alright, as I mentioned before, hydrocarbons tend to be isomeric, meaning that they have a lot of different structures, but the same chemical formula. So there are a lot of possibilities for C4H4. However, as long as you follow the octet rule and you don't have any missing or extra electrons, I will give you full marks for your drawings, even if they are unstable or don't exist. You will learn which molecules are more likely to exist, more stable, in future chemistry courses. Alright, so let's begin. C4H4. So I'm going to draw my carbon backbone, and I know that each of these carbons should have 4 bonds, because they each have 4 valence electrons. Unfortunately, I only have 4 hydrogens, so I'm just going to put them here, 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 and here. Doesn't really matter. But look at all these empty spots. What can I do with them? They can't just stay there opened. They have to be bonded to another atom. When this occurs, you might want to try making multiple bonds, double bonds or triple bonds. So I'm going to collapse these two together, and in the process forming a double bond here. And I can do the same over here, collapsing these two, creating another double bond, and guess what I'm going to do over here? Another double bond. Now let's double check, are each of these atoms stable? So the hydrogen should only have 1 bond, 1 bond, 1 bond, 1 bond, 1 bond, while the carbon should have 4, 1, 2, 3, 4, and this carbon, 1, 2, 3, 4, this carbon, 1, 2, 3, 4, and same thing with this carbon, 1, 2, 3, 4. Remember, each line represents 2 electrons, so hydrogen gets 2, and these carbons get 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So this is just one possible structure, but this is another one as well. So remember, you can also make ring structures. Over here I did the same with another ring structure, C4H8. So 1, 2, 3, 4, 4 carbons. 8 hydrogens, 1, 2, 3, 4, 5, 6, 7, 8. Do the hydrogens each have 2 electrons? So 2, 2, 2, 2, 2, 2, 2. That's good. Do the carbons have 8 electrons? 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So that's one possibility. And here's another possibility. 1, 2, 3, 4, 4 carbons. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. And do each of these carbons have 8 electrons? Yes. Now this one's interesting. C3, so I put the 3 carbons side by side as my backbone. H5, I gave each of these ones an H where I could. And then this one was left open and a nitrogen at my far end. Now the hydrogens are all stable with 2 electrons each. And these carbons are fine, 2, 4, 6, 8. 2, 4, 6, 8. But this carbon and this nitrogen are not quite at the octet structure yet. This carbon has 1, 2, 3, 4, 5, 6 electrons, while this nitrogen has 1, 2, 3, 4, 5, 6 electrons as well. So both of them need 2 more electrons. As I mentioned before, situations like this usually indicate that you're going to have a multiple bond, either a double or a triple. So if I need 2 more electrons to bond, I can just connect these two over here. As such, we have a triple bond between the carbon and the nitrogen. So if I clean this up, you'll get something that looks like this. So once again, I see a CH3, and that usually looks like this. It's then connected to a carbon and a nitrogen. Now, we've seen this pattern before, and that usually means that a triple bond is present. So cleaning it up, we look like this. Alright, over here I see a CH2, not a CH3, so I'm going to put a C and H2. Next there's going to be a carbon, so I'll put that down here. But then there's a hydrogen. But if I put the hydrogen here, I can't go any further, because remember, hydrogen can only make one bond. It only has 2 electrons with it, and so this is kind of a dead end. But based on this formula, I know it can't be a dead end. I have to have another carbon next to this. But it would not be allowed to be sitting next to it, because now hydrogen has 4 electrons around it, when it's only supposed to have 2. So rather than putting the hydrogen here, maybe I can shift it to here instead. Now I have the ability to continue the chain to put another CH over here, followed by an oxygen at the end. Alright, so let's check this out. This carbon is not stable because it only has 2, 4, 6 when it should have 8. So it's got a lonely electron here that needs to be partnered with someone else. We've got the same problem with this carbon, 2, 4, 6. It should have 8 electrons, so it too has a lonely electron floating around. Well, guess what? Lonely electron here, put them together, and they're lonely no more. Now take a look at this carbon. One electron is bonded with the hydrogen, another electron is bonded with this carbon, so that's 2 of them, but carbon should have 4 electrons. So I'll put them in here and here. So right now this carbon has 2, 4, 5, 6, 7 electrons around it, and this oxygen has 1, 2, 3, 4, 5, 6, 7 electrons around it as well. They both need 1 more, so let's connect these 2 together to form a double bond. I'm going to clean this up, and there's our structure. Now we haven't encountered a bromine yet, but bromine has 7 valence electrons. CH3, no problem, you should recognize that pattern now. CH2, CH2, and then a bromine at the end. This bromine with 7 electrons needs 1 more to be stable. This carbon, also with 7 electrons, needs 1 more to be stable. So we connect those 2 in a chemical bond. And now the carbons and the bromines all have an octet structure. So over here I have that CH3 again. I have a nitrogen over here with 5 of its valence electrons, 2 hydrogens each attached over here, and so now we've got 2, 4, 6, 8 electrons around the nitrogen, 2, 4, 6, 8 around the carbon. Everybody's happy. Let's clean this up, replacing the bonding pair electrons with lines, and there's our structure. Just like bromine in the last example, chlorine has 7 valence electrons, needs 1 more, so I place them all around the carbon so they can share their electrons. Now this carbon has 2, 4, 6, 8 electrons, so it's got the octet structure. So do each of these chlorines. This carbon over here has 2, 4, 5, 6, 7, so it needs 1 more. And this oxygen here has 2, 4, 5, 6, 7, also needs 1 more. So we're going to connect these 2 together to form our double bond. Let's clean this up, replacing our bonding pair electrons with lines, and this is our structure. So again, CH3, CH3 with an NH in the center. I can now connect these bonding pair electrons, and there's one possible structure. Over here I have an NH2, so NH2. On the other side I have a CH3, CH3, and in the middle I have a C and an O. As we saw before, we can make a double bond here by connecting these 2 together. And now all we have to do is clean it up, and we're good to go. Alright, in our next video tutorial we will cover physical properties of ionic and covalent compounds.